This presentation is delivered by the Stanford Center for Professional Development.
So, welcome to EE 263, and I guess I should say for many of you, welcome to Stanford. Well, as I said, this is EE 263. I'm Stephen Boyd, and I'll start actually just with some. I'll cover some of the mechanics of the class, and then we'll start in. Today is just going to be sort of a fun lecture, so it's not representative of the class. So by the end of the, you'll notice you'll leave thinking, well, it was interesting, but it was kind of like content free. Anyway, trust me, it's not representative of the quarter. So, what's that? Aha! Ah! Wow! Is there finally a room so big that I'm not loud enough? How about you people in the back? Can you hear me? Wow. Oh, I can be loud. We'll try it. We'll go natural until you tell me you can't hear me or something like that. So, okay. So let me just say a little bit about the mechanics of the class. I should introduce. We have at the moment we have 2 TAs that will grow by the end of the day to 3 and maybe 4 later. There's Jacob Mattingly over there. Young Wong is here, and we'll have hopefully we'll have another 1 or 2 within a day or so. So let's see. I'm trying to think what else. What else is what the important things are to say about the course that are just mechanics. I'll get into prerequisites and things like that soon. I do have to make one announcement. Maybe it's even legally required. I'm not sure, but Stanford is going to experiment with putting this course in particular online, open to the world. Strangely, this is going to be after a 1/4 delay. So that means this course will go online everywhere in a quarter. Now that's interesting because that means if you ask, well, right now the way it works is this: if you ask a question now in the class, and it's a dumb question, then of course, as you know, it's on streaming video. That means that your roommate or mates can go back and replay your dumb question multiple times and laugh. You know, but that's only 30,000 people at Stanford who have access to that. So if we go online, though, of course, that's a lot more. And of course, it means it's entirely possible that you'll end up on YouTube. You know, maybe I will. Who knows? We'll see what happens. So anyway, but to put you at ease over that. If the camera, I guess they were saying one of the things they have to do is they have to clear copyright and things like that before they put this on well, open to the world. By the way, the course notes and course materials have been open to the world forever because I control that, and it's always been open to the world. Now I'm actually talking about the lectures. So what will happen is I think if you do ask questions like that, rest assured your face will be all fuzzed out, and they'll change your voice too. So go ahead and feel free to ask any question you like, is what I'm saying there. But there, I think, who knows? It's an experiment. We'll see how it works. I'm going to forget about it. It's going to be interesting for us. The other courses doing this are EE 261, a couple of CS courses and things like that. And so we all looked at each other and thought, what have we gotten into? We're going to have to behave. That's going to be very difficult. But I think the way that's going to work is they'll be edited. So if, for example, you are watching this, it's February right now. Maybe this part will all be edited out. But the way you'll know when something interesting happened in the class is all of a sudden my head will go like this. There'll be a little continuity glitch there. And that'll mean that something we said needed to be edited out. So, okay. So let me just jump, maybe I'll just jump right in and cover the course mechanics. If you can go down to the pad, that would be great. Great. Okay, so I'll start by just going over the course mechanics. I'll say a little bit in very broad brush what the topics of the class are. It seems odd to have to not say what a linear dynamical system is, since that's what the name of the class is. Actually, what's interesting is I'll say what it is, and we won't come back to that topic for several weeks. I'll say a little bit about why you'd want to study the material in this class, and then we'll look at some examples. So first of all, in course mechanics, I should say this. Everything, with the course website, oh, by the way, we do not use EE class. So if you want to go there, that's fine. You'll just find a frame that has the real website. Okay, so we don't use EE class or anything like that. It's just the website where you'd expect the course, all the course materials to be. And we try to make the website basically the most accurate source of information. After the website, I would say the next most accurate source would be the TAs. After that, only if you're desperate, me. So if I say something and the web says something different, it's more than likely that what's on the web is right. So just to let you know, that's how we do this. We also correct typos and things like that almost in real time. And then we deny that the typos ever existed. Okay, so that's just to let you know, that's the policy. So you'd say, excuse me, there's a minus sign here, and I'll say, nope, no, there's not. And you can look on the web, and all you have to do is refresh. If you refresh, the minus sign will just go away, and everything will be back to right. So that's how it's going to work. Okay. So I should add for the reader, the PDF file for the entire reader is available online. In fact, my understanding is that the bookstore charges some idiotic fee. How much did this cost? Do you know? $30. I think that's kind of ridiculous. But anyway, that's fine. Maybe we'll find another way to print it next year. But the entire reader is available as a PDF file. All the homework, just everything is available on the website. Everything will be available there. So we also fool around a little bit sometimes during the quarter to see how often people are checking the website. So we'll post things that are incomplete, links that go nowhere, just to see, like, we'll do it at 1 a.m. to see like what. Anyway, we did that experiment last year, and I think we got to like 1:20 a.m. before somebody said, hey, your link doesn't go, you posted this, but the link isn't there. So we do that just for fun. Okay. So the course requirements are going to be weekly homework. So the homework, tentatively, we're going to be on a Friday cycle. So the first homework, which incidentally is assigned, and you'd know that by looking at the course web page. So the first homework is actually assigned. I won't even say anything about it. I won't come in and say, oh, by the way, homework 3 is assigned. It'll just be on the web. So homework 1, which is assigned, will be due next Friday. So we may have to adjust that because there'll be a section for the course, sort of a problem section or whatever, which is not required, but it will also be televised. That means that we have to go to SCPD. We have to find a room that's television ready. So we don't know exactly what day that will be, and we may have to adjust the schedule a little bit around that. So that's why I think even right now there are 2 places on our website we say that the homework is due Friday, and another place that mentions homework is due on Thursdays. When we find a room for the section and announce it, then everything will be set after that. The things like TA office hours will be set. Let's see, what else will be set? The section time, all that sort of stuff will be set. Hopefully we'll be able to do that in the next day or 2. That would be great to get that ready. For the homework, actually, I would not only are you allowed to work together, but actually I would encourage you to work in groups, in small groups on the homework, and it has to be some kind of group that makes sense for you, because a lot of the homework it's easy to kind of do it. It's actually, if you really want to know if you understand it, you try to explain it to the other person or 2 people you're working with. If they're kind of looking at you kind of like this, that means they don't know what you're talking about, and that means it either means you don't understand it or you haven't explained it that well. So that's a very good way. Oh, and by the way, that means when you're playing the other role, when someone you're working with is trying to explain it to you, don't be polite. If what they're saying doesn't make any sense to you, just say, interesting. But that makes no sense. So that's how I would, I'd encourage you to do that. The homework will take a lot of, it should take a lot of time. I don't know what an average amount is. I mean, I don't know, 10 hours. I don't know, honestly. Because then you can't ask people. It's sort of a biased sample. And, you know, some people they know it'll insult me if they say, oh, I do it in 90 minutes or something. And others go on and say, oh, no, it took me 25 hours. I don't know which to believe. So it's somewhere in between those two. It will be graded very crudely. So, and I think, you know, you just do the arithmetic. If you multiply the number of people in the class, these homeworks they're big, thick things. They will take you a lot of time and effort to do these. It doesn't count a huge amount into the grade, but this is graduate school and grades don't really matter and all that anyway. And they'll be graded crudely. So I think the official amount of time is something like 15 minutes. So you'll take, let's just say you take 6 hours to do the homework. Let's just say 8. Someone's going to go over it for 15 minutes. Now, you know, that might strike you as odd or something. But you do the homework so that you can learn. That's actually, I believe, where you do the real learning is in the homework. So although it doesn't count a lot for the grade, it will be looked at by a grader briefly, very late at night, for 15 minutes, max. But still, it's very valuable, just having done it or anything like that. What that means is, you know, please don't come to us later and say, you know, I think, you know, gee, the grader didn't get some subtle point in my argument here. Because basically, like, I got news for you. The grader looked at this between 2:07 and 2:14 a.m. on Tuesday. So it's likely that the grader didn't. But anyway, so OK. We'll have 2 exams. There's going to be these are both take-home exams. You may already have heard about these. Actually, I'm just curious how many people have heard about these. Oh, good. And what have you heard? Were you pointing down or? No, what was that? That was a down. That we had something pointing down. But now wait a minute though. But then why are you here? Don't know. Okay, sort of self-destructive instinct or okay. All right. So actually, these are fun. These are take-home. These are take-home exams. They're nominally 24 hours. People rarely take over 20 to do them, but they do sometimes, and they're fun. They're now an institution. We actually even tried to change it, I think, like last year or something like that, and students from previous years came back to protest to say that no, you couldn't possibly do this. It's part of the whole experience, and so on and so forth. So anyway, so that's how we'll do that. And we every now and then I just ask people if they'd be interested in any other format, like how about 48 hours, and that people are like no. And I think shorter is silly, so that's how it's going to be. Oh, I should say that there's something very important here for scheduling. The take-home exam, traditionally, and I should also say illegally, is scheduled for traditionally the sort of the end of the last week of classes. Okay, so there is an official exam date for this course. I forget when it is, December 4th. I'll probably already be in Hong Kong, by the way, at that time. So we do it sort of at the end of the class. That's totally illegal, according to the university. But, you know, they know where I am. They can come and get me anytime. That would be good, actually, to have posted on the web. Would be to have I don't know what the police unit for the registrar's office is, but that would be good, actually. Anyway. All right. So what this means, though, this is actually very important. I've already gotten a couple of emails from people who are making, you know, flights home or whatever. And don't, basically, as early as you want to leave, I mean, assuming it's not in the quarter, we will work around it. If you're leaving literally like the week after classes finish, no problem. You're a beta tester for our final exam. Okay, so we'll work around you, just to let you know that. Okay, this is all just mechanics. Any questions about the mechanics, how it'll work? Did I forget anything? The only thing I might have forgotten is there won't be a section this week because well, we don't have a room. So next week will be the first week there'll be a section. We don't know what day it will be or where it will be, but that will be announced on the email list, and it will also go on the website. So, okay, so now we've covered the mechanics. Let's go a little bit into, I'll say a little bit about the prerequisites for the class. That's actually important. So the first is that you should have had an exposure to linear algebra. These words are actually chosen very carefully. You typically, in this class, there are people who have there's a very wide range of backgrounds in linear algebra. All the way from essentially none, from people who said, oh, I took a course on multivariable calculus. I think I know what a vector is and a matrix, all the way to people who've taken multiple courses on linear algebra. So in fact, what you really need is just something like an exposure to it. So if, you definitely should have seen vectors, matrices, hopefully ideas like rank, range, null space. However, since linear algebra class are, by tradition, extremely boring, it is natural that you should have either hated these courses and actually suppressed the memory of those courses as much as possible. That's natural. In the first part of the course, we will be going back over this, and that means, of course, that painful memories will be coming back, but there's lots of us here, and we're all doing it together. So everything will be fine there. I should also say one other thing here. Something different this year, actually it started last year. This course is now offered twice in the year. It's offered fall, but it's also offered in the spring. And that actually is very important. It means that if you decide somewhere into the class, a couple weeks in or when, I don't know when, couple weeks in, that in fact what you'd like to do is actually take this in the spring and maybe take something like Math 103, or I don't mean really Math 103, but that's if you could just look on the course catalog and see what's involved there. If you want to defer, just sort of take that and then take this in the spring, that's an option for you. That wasn't an option in the past, and that was a problem because people sort of didn't drop out saying they could do it. Now, having said that, a lot of people actually just do fine. I should also make a comment to those who come in with a much stronger background. So there are people who come in with a much stronger background in linear algebra who've had maybe an entire course or whatever several years ago. So that's fine too. Actually, there the reaction will be that somewhere around the fourth week, you might be thinking something like, when am I actually going to learn anything I don't already know? Actually, trust me, you will, because this is different from the class you took, I promise. And in fact, all those people actually come back to me later, not all of them, but most of them come back later and say, you're right, I learned something. So, okay. The only other real prerequisite, and this is not even really a prerequisite that much, is at just a few tiny places in the course, we're going to use the Laplace transform differential equations. This actually, even if you hadn't seen this, but it would be difficult for me to believe that you haven't. Again, we'll cover all the background material needed for this. So that's really the formal prerequisite. This not a whole lot else. Now, the course, this material, I'll talk about this soon, is used in tons and tons of areas. But in particular, you do not need to have taken a course on like control systems or something like that, which is one area. You actually don't even have to have taken any course on circuits and systems or a course on dynamics. So you could be, it would be fine. We will look at examples sort of taken grossly from control systems, circuits and systems, dynamics. We'll also look at examples from machine learning. There'll be examples from signal processing, communications, networking, all over the place. We'll take care that you don't actually need to know anything about these application areas. I mean, these are really more like little vignettes where you just kind of oversimplify it and show it here. That's just, so don't worry if you see things like that. In fact, today you will see things like that. Don't worry about it. whenever it matters, we'll make sure everything is needed. So the point is that although it's perfectly okay for you to have had a course on control system circuits and systems dynamics, for that matter, machine learning, signal processing, it's absolutely not needed. So, and I know every year we have people in this class from, for example, economics, from all sorts of areas. Doesn't make any difference at all. So, okay. So let me say a little bit about the outline. The first chunk of the class is basically going to be a review of linear algebra and applications. I'm going to sort of assume that you've already had a class where somebody droned on and on about rank and range and the 4 fundamental subspaces and things like that. So this will actually be about modeling and applications. So it's actually, where does this actually come up? Where do you use this stuff? And that's actually the theme of the class. Let's see. Then we'll talk about autonomous linear dynamical systems. I'll actually say what those are shortly. Then we'll move on to systems with inputs and outputs. And then we'll look at sort of basic quadratic control and estimation at the very end of the course. But in fact, this is really an application if you've understood the material before. OK. So maybe at this point, it's time for me to say what the class is about. Although, we'll drop this topic and we will come back to it only in about 3 or 4 weeks. So what's a linear dynamical system? Well, a continuous time linear dynamical system looks like this. It's a vector differential equation. So it looks like dx dt is a of t, that's a matrix, times a vector x of t, plus b of t times u of t. That's a vector, that's a matrix, and I'll talk a little bit about, oh, this reminds me. On the course website, there are some extra notes. There's quick notes on matrices. There's like, you could just read them literally 30 minutes. Please take 30 minutes and read them. So, because first of all, it's going to say that these are things I will use without ever, I will not go into them. I won't mention. It's just, and the other thing is, if the notation you saw was slightly different, this would set the notation straight. Actually, I kind of try to use, sort of a high BBC level of mathematical notation. So if you saw notation that's substantially different, that's because what you saw was weird and strange. So maybe it was in some other weird field or something. So throughout the class, I'll make fun of other fields periodically. No, I don't think I get to do it today. So OK, but we'll get there. OK, so here, typically, t, as the choice of symbol suggests, is going to represent time. Of course, it need not, but it will represent time. Here, x of t, that's this vector. Actually, it's a vector function, and that's called the state. That's a vector. Sometimes, colloquially, the actual entries of x will be called informally the states, like that. So that would be the ith state. But that's slang, and you should know that. That's xi of t. U of t is called the input or control. It depends on the field you're in. We'll talk more about that. And y of t here is called the output. I think this equation is sometimes called the dynamics equation. And this equation is sometimes called the measurement or readout equation. It's got all sorts of names. And then all of these matrices here have names. You don't have to remember any of this because I'm going over this just so that you can't, otherwise we'd go 4 weeks into the class and someone would ask you, how's the class going? You say, it's great, but we haven't even gotten to what the title of the class is. So, OK. So this matrix A of t is called the dynamics matrix. Here, B of t is sometimes called the input matrix, C is called the output or sensor matrix, and D is called the feed-through matrix. We're going to come back and go over this again in horrendous detail when we really get to this. So you don't have to remember any of this or all that sort of stuff. OK. Now, this is too ugly, so it is often written in this very simple form that looks like this. It's x dot is ax plus bu, y equals cx plus du, just like that. Where you suppress all sorts of things and have them understood. So a linear dynamical system is nothing but a first-order linear differential equations, nothing else. Now, there's other names for this. These are called state equations. There's all dynamics equations. They have all sorts of names. It depends on the field you're in or what application area you're in. I should also mention that A, B, C, and D are traditional. You can usually tell where someone got their PhD and so on and so forth by their choice of notation. For example, I think there was someone who taught at Stanford in aero-astro for a long time, and that was x dot equals fx plus gu. So that turns out that's because he got his PhD at MIT in 1967 and got it from some, picked this up from somewhere. So you will see other conventions here. I mean, of course, it's nothing but notation, but just to warn you that you'll see that. But if you ever see someone who writes down x dot as fx plus gu, it probably means they went to MIT or something like that, or took the class from someone who went to MIT. But now they've switched to this too anyway, so it's complicated. Okay. So let me mention a couple of things. Many, but actually not all, and we'll say something about that later, are time invariant. So that means that these matrices A, B, C, and D, they're constant. They do not depend on time. Now, if there's no input, that means so there's no B or D matrices. The system's called autonomous because essentially it goes by itself and has nothing to do with what U is, which is usually interpreted as some kind of input or something like that. And very often there's no feed through, so you get things that are very, very simple. Now, some notation you'll hear is this. If these inputs and outputs are scalar, the system is called single input, single output, and I think the slang for that is SISO. When you have multiple ones, it's MIMO. Now, this is a bit silly, frankly. I mean, this is kind of a holdover to when it was really a big deal to have, like, 2 inputs and 2 outputs. Even other fields, like, communications and things, signal processing, are now getting used to the idea that you typically process more than one signal at a time from more than one measurement or from more than one input. So in fact, I guess wireless communications is going through the very end of what I'd call the MIMO stage of development. So this was very hot 10 years ago, and it was a big deal, and people get all excited, and you'd say, wow, what's that? And they go, it's unbelievable, it's amazing, it's totally amazing. Instead of holding up like one antenna and looking at the radio signal coming from it, are you ready for this? We're going to hold up 2. Unbelievable. Can you believe this? Got it? Actually 2. And we'll take those 2 signals, and by processing them right, we'll increase the capacity of our cell network. Anyway, other fields have been there, done that decades and decades ago. There's still fields that haven't, by the way, reached the MIMO stage. They will. It'll be happening soon. Sooner or later. Okay. So, okay, let me say something about discrete time. This, what we looked at so far was a continuous time. Let's look at discrete time, linear dynamical system. So that's nothing but a recursion. So here, instead of a derivative, it's simply an update equation. It says that the next state is obtained by multiplying the current state by a matrix A of t. And to that you add something which is related to an input. Here the time is an integer. So it's a discrete time thing. And sometimes the time is either called, it could be a sample. It could also, sometimes people call it a period. For example, in economics, you would talk about periods. These could be trading days, could be anything. Okay? Or this could be some audio signal processing, in which case these are samples at some standard rate, like 44.1 kilohertz or something like that. Now in this case, the signals are sequences. In the continuous time case, signals are functions, and I'll say a little bit about that. So it's nothing but a first order vector recursion. Okay, that's done. What I just explained, there's no way anybody would have gotten any idea of what they are, but at least now you cannot say I didn't tell you what a linear dynamical system was on the first day. I've done it. We're going to come back and we'll be going into this in horrendous detail later in the quarter. So let me say a little bit about why would you study linear dynamical systems? Well, it turns out the applications, they come up in, nowadays, it's just it's everywhere, absolutely everywhere. So, I mean, sort of historically, the first application was in automatic control. This was aerospace maybe in the 60s. That would be the first sort of real application. Now, at the time, it was super advanced. super advanced technology, very, very fancy. It hit signal processing, let's say, mainstream signal processing, let's say about 15, 20 years ago is when it hit signal processing. So until that time, signal processing, and indeed, I bet your undergraduate exposure to signal processing just fiddled with a scalar signal. Actually, for how many people is that the case? Actually, how many people took signal processing? Okay. And for how many of you did you ever hear of a vector signal? Cool. Really? Where? Cool. That's okay. There were just a few others. Where were some of the others who heard of a vector signal processing? Where? Caltech. Well, okay. Times are changing. That's really cool. Okay, great. So what you will find, actually, is except for undergrad signal processing, almost all signal processing now involves linear dynamical systems in one way or another, or something like it. All of it. So all signal processing pretty much involves ideas from linear dynamical systems. Communications, I'd say it hit big time about 10 years ago. Although, in fact, in communications, there was always some stuff that went back into the 40s and stuff like that. So communications is another area. Economics and finance, it's totally basic. If you look at evolution of an economy or something like that, comes up all the time. In finance as well, most of the models are just linear dynamical systems. Some of the notation will be different, but it's very close to what we'll be looking at. Circuit analysis. So it may not be linear dynamical systems, but linear dynamical systems actually plays an important role, very important role in circuit analysis, circuit simulation, and also circuit design comes up a lot. It comes in mechanical and civil engineering. You see it in things like dynamics of structures and all sorts of other stuff. Aeronautics, it's everywhere. It involves dynamics, control, navigation, and guidance. So for example, GPS. So things like this are all done using this, well, the stuff you will see in this class. A few other things you won't see, which reminds me about something I didn't say. Here's a topic that maybe should be a prerequisite, but actually is not. And that's actually probability and statistics. So I think that's kind of weird that we don't have it that way, but it's not a prerequisite. So just to let you know. Occasionally, I might refer to things that involve probability and statistics, but technically, that is officially just a side comment. That's just for those who know what I'm talking about. So actually, if you combine the material of this course with sort of probability and statistics, now you're getting close to actually what is used in tons and tons of fields. By the way, it comes up in other areas like machine learning as well, is another one. Okay. Now, the usefulness of the material, it scales with available computing power, which thanks to other people in EE and materials and areas like that, has been and is and will continue to scale by Moore's law. So that's great because that's sort of the difference between this material in 1963 and this material now. There's a huge difference. Now you can actually, in 1963, you could do this stuff, and there were people who did, mostly militaries. Now, anyone can do it. It's widely used. It's widely fielded. And that's basically entirely due to increases in computing power. The computing power is used for analysis and design. But it's also used for implementation and actually just embedded in real-time systems. And occasionally, I'll make some comments about that. And I do want to say something about how courses evolve. So especially sort of, courses on mathematical type, engineering type stuff. So digital signal processing, I guess maybe the first class ever given was maybe at like MIT in like 1956 or something like that. And it was this super advanced class with maybe, I don't know, four PhD students in math in the class. And sort of, for a decade or two, it was this ultra advanced course. It was ultra high-end technology that the only people who would field this would be like, you know, the military and a couple of other, you know, maybe some banks or Boeing or something like that would do it. But DSP, as you know, that's now like a core undergraduate topic. I mean, it's just everywhere. I mean, so that's how that went from super advanced, you know, more, you know, advanced PhD level class 30 years later, again, thanks to technology. 30 years later, it's now like, you know, your basic, it's your second course. In fact, in some places they're switching it and they're making it the first course an undergraduate sees in, for example, electrical engineering, which I think is a good idea, right? Because soldering skills are, well, they're useful, sure, but maybe less so. That moving forward, I can solder, by the way, just if you're thinking, if you're curious. Okay. Okay, so what are the origins in history? I can say a little bit about this. So part of it, you'll trace to the 19th century, and you'll hear names, you know, that are names of 19th century mathematicians. So the linear algebra itself, that all goes back to, you know, 19th century, early 19th century even. But it sort of blends sort of classical circuits and systems. This would be from 1920s on. This would be the stuff done at like Bell Labs in the 20s. So it kind of combines that with linear algebra. So that's kind of that's what the modern form is. Now the first time you could say, you know, here is linear dynamical systems actually either being taught or being used or whatever, is actually is aerospace in the 1960s. So and that would be the first time it was widely used. It was used for at that time I think you'd have to say it was not used for what we would call socially positive purposes. It was used to land missiles and things like that. So that was aerospace in the 1960s. Very, very fancy stuff. But between then and now, somewhere in the 80s, it transitioned into from a specialized topic, which 12 or 15 PhD students would take, to one that basically touches all fields, and not just all fields in EE, but also other fields in optimization and finance, in economics and things like that. So that was sort of the transition time. And this is, I've already said the story of digital signal processing. DSP is the same. Another story, you can go back down to the pad here, is information theory. That's the same story. That information theory, as you know, was more or less created by Shannon in the late 40s, but in fact also by Kolmogorov in the Soviet Union in Moscow in about the same time, maybe even a bit earlier in that case. It was created there, and the people who actually did sort of communications just fell down laughing, saying, like, what is this a joke? We could never use that. Like, get out of here, Mr. Theorist. We actually have work to do here. So, of course, the joke was on them, because you propagate Moore's law forward a few decades, and you'd be surprised at what you can do now. So information theory is now not just a super advanced esoteric topic. It's a topic like basically everybody needs to know about, and it is widely used. Okay? So, I mean, it's still also there's a vibrant theoretical core, but it's not just a weird thing done by, the 15 PhD students who make this their topic. It's something like everybody ought to know. So, okay. I'll say one more thing about this. I'll say a little bit about nonlinear dynamical systems. You hear a lot about this, and I'm deeply suspicious of these people for many reasons. I'll tell you why in a minute. But so it is absolutely the case that many systems are nonlinear. And not only that, nonlinear dynamical systems is a fascinating topic. I don't deny it. So if this is the case, why should you study linear dynamical systems? Well, I'd make a couple of arguments for it. The first is that it turns out that most methods for nonlinear systems, for engineering things that work for nonlinear systems, basically are based almost entirely on ideas from linear dynamical systems. And in fact, there's this weird thing where you design things based on linear models that are not even remotely accurate. And unfortunately, I'll explain why I say unfortunately. Unfortunately, these things, more often than they should, work. See, I don't think they I'll tell you why I think they shouldn't. Because it reinforces kind of cowboy engineering is what it's kind of like, you walk up to someone and say, what are you doing? You say, I'm designing, a regulator for this thing. Is it linear? Oh, no, not even close. And you go, but what are you doing? And you say, I'm pretending it's linear. So every now and then something like that should blow up. I mean, just look, maybe just singe the person who did it a little bit. But the point is just to send a message, which is, you should kind of know what you're doing, or at least respect, or at least when it works, step back and say, wow, that's cool, because it didn't have to work, but it did. So but unfortunately, these things just often work, even when the models are way off. It's known a little bit why that's the case, but it's just a reason to study linear systems. The other one is that actually, if you're really interested in nonlinear dynamical systems, then it turns out, if you don't understand linear dynamical systems, this is the big prerequisite as far as I'm concerned. And the other thing is, it's funny, you get people who, there's like a little cult following. This is why this would be the chaos crowd. And you can go to the Santa Fe Institute, this place, and people will tell you all about this stuff. I can fool any of them. Give me 5 minutes with any of them. I can fool any of them. They'll say, oh no, linear system's not interesting. You can't have, you can't have bifurcations. You can't have chaos. You can't have blah blah blah. Anyway. It will take me 5 minutes to put together a linear dynamical system that will totally fool them. And they'll go like, oh yeah, that's chaos right there. That's chaos. But it'll just be some linear system. So anyway, that's just my ideas. You'll hear about this, okay? And actually, it's really interesting stuff. But okay, so that finishes up my kind of overview of the course. I don't know. Are there any questions? It'd be kind of hard to have a question because I didn't say anything. But there might be a question anyway. I guess not. Okay. So, okay. What I'm going to do now is for the rest of this lecture, I'm actually just going to go over some examples. Now, this is ideas only. There'll be no details. I do not expect you to understand any of it. All of this we will come back and do later in the class. All of it. In horrendous detail. So don't try to get everything now. Okay. So what we're going to do is just look at here's a specific system. It's x dot equals ax. Here, the state vector has dimension 16. And we have a scalar output, y of t. So people on the slang would be this would be a 16-state single output system. Now, it turns out this is a model of a lightly damped mechanical system, but it really doesn't matter what it is for now. So, but if you want a physical picture of what this is, it is a mechanical system with sort of 8 generalized positions, 8 generalized momenta or something like that. So it's some kind of like structure. And the dynamics is what happens when you poke it. For example, if an earthquake excites it. And then the whole thing kind of wiggles around. And this would be, the output would be the specific displacement in some axis at some point in the structure. So that's what, if you want a physical picture, but you don't need one. So here's a sort of the typical output, looks like this. And the first shows what it looks like on a short time scale, or shorter time scale. And then this is what it looks like on a longer time scale. Now, the point about this is this looks it looks quite complicated. In fact, if I showed you, let's say, just the first 100 samples, just that right there. If I showed you that and said to you, I didn't tell you where it came from, but I said, here's a signal I've observed. Would you mind predicting it? Now, if I asked you to predict it, 1 or 2 samples in the 1 or 2 seconds or whatever the time unit is here in the future, you'd say, yeah, no problem, I'll make a prediction. But what if I said, would you mind, having seen this, predicting what this will be doing at t equals 1,000, right? You would hopefully look at this and say, are you insane? I mean, that's I don't even know what that thing is. It's weird. I mean, it's some weird thing. And it looks like it's changing character over the 50, let's call it seconds, over the 50 seconds you've shown me. How on earth would I be able to predict what it does 1,000 seconds later? Everybody see what I'm saying here? Okay. for sure. This is not long enough, but I could get one. I could definitely get somebody at the Santa Fe Institute to go for chaos here. No problem. They could say, oh yeah, I'm seeing it. I'm seeing period doubling, bifurcation. It's all there. So, okay. So the point is, you could make all sorts of stories up about this. You look at a longer time scale, you could say, well, it started off chaotic, but now you can see there's some kind of regularity emerging from this. It's, you could make all sorts of stories. So out here, in fact, it would seem reasonable for someone to predict, if you saw this, what's going to happen for another 100 seconds or so. It would seem reasonable because some kind of periodicity or something or pattern has set in. Everybody see what I'm saying? Okay. Now, this is hardly surprising, but it turns out, and this will be familiar to you from the idea of like poles and things like that, that this output, and indeed the output of any linear dynamical system, it can be spectrally decomposed. It can be decomposed into modes or frequencies, complex frequencies. And the exact one I just showed you, actually, we can write it out this way. There are 8 of these. And if you were to add these 8 signals up, you would get this one here. Okay? Now, this should hardly be surprising to you. I mean, you've sort of seen this, maybe, or some of you have seen this in other courses and things like that. But there's actually, once you know that this is the case, it's a totally different story. If I were to take this signal and decompose it like that, and I now said to you, please make a prediction about what this signal will be doing 1,000 seconds in the future, you would probably say, no problem. Because each of these is just a damped sinusoid. And you have a few parameters to fit for each one. That's something else you'll learn in this class. You'd have a few parameters to fit, at which point you could probably quite easily extrapolate it. Okay? So again, this is probably not too, it's not too shocking. Okay. Now let's look at input design. Input design goes like this. I'm going to add 2 inputs. So I'm going to add 2 inputs. Now, by the way, if you're visualizing a mechanical structure, and we're going to have 2 outputs, by the way. So you can imagine a mechanical structure, and I want to put, like, let's say 2 piezoelectric actuators on it. I mean, or if you want to make the time scale big, a whole building, let's put 2 hydraulic actuators on it, or something like that. But let's make it 2 piezoelectric actuators on something that is small, that sits here. I have 2 actuators, and then I measure the displacement of the thing at 2 other places. Okay, so I have now a 2 input, 2 output system. You should have a very good idea of what happens when you put a force or a displacement input onto a structure. It will start shaking because you'll excite various modes. And eventually, if it's got damping in it, it does, it will sort of come to rest. And those 2 points will have been displaced if the input has a constant value or something like that. So here's the job. We want to find an input that brings the output to some desired point. 1 minus 2. This is totally arbitrary, but since you don't know what A and B is, it's probably not relevant what the output is. So you want to bring this output here. And so your choice now, this is a generalized, this is like a design or a control problem. It's choose an input or action that makes something you want to happen. Okay? So that's what you're being asked to do. By the way, this is quite a realistic problem. Any disk drive has stuff like this in it, where you get a command for the head to move from track 22 to track 236, and to do it and be tracking in some very small number of milliseconds. Okay, so this is quite realistic. If you change the time scale and all that kind of stuff, this is actually very realistic. Okay, the problem. Okay, so here let's just look at the simple approach. The simple approach is this. Let's assume, if you wait for the whole thing to come to equilibrium, that means everything's constant. That means x dot, which is dx dt, is 0. So you have 0 is ax plus b u static. I'm putting in a constant input u. By the way, don't try to follow this. We're going to go over all this later. And then the output is also constant. You can solve these linear equations by simply putting ax on the other side. So you have ax equals bu static minus BU static, you multiply by A inverse on the left. But I won't go through the details. But what you find is you can actually simply work out a formula for what the optimal, what the input should be. Not optimal, the input. The input required is this. So let's imagine then that these are, say, piezoelectric displacements. So one of those piezoelectric actuators should pull in, and the other should push out. And by doing that, that will twist the structure in equilibrium so that whatever the one is displaced, let's say 1 millimeter to the left, and the other is 2 millimeters to the right, or whatever this means. Okay, so that's the idea. Okay, let's just go ahead and apply that input. And let's see what happens. This shows you a little bit of negative time. The u's are 0, and right at t equals 0, we simply apply this thing. So you have a structure, and at t equals 0, one of the piezoelectric actuator shrinks instantly, the other one pushes out. And of course, that causes everything to start shaking in this structure. So everything shakes. And this is what the outputs do. You can see they shake for a while, and about 1,500 time units later, they are converging indeed to what they're supposed to, 1 and minus 2. Okay, so there it is. And you could now make all sorts of arguments about this. You could say, well, look, that's the basic dynamics of this system. I mean, come on, the thing shakes. It takes whatever, 1,500 seconds or picoseconds, depending on what application you're thinking of, or microseconds. It takes 1,500 microseconds to just get the energy out of the system, to have it dissipate. So how could it ever be any faster? Okay. Well, later in the class, we'll look at problems like that. And it turns out you can do a whole lot better. So here are some inputs. Here's one, and here's what you do at one actuator, and here's what you do at the other. And this one, I mean, this is really pretty bizarre. This ends up pushing at minus 0.6, but the first thing it does is it goes in the opposite direction. Same for this one. Then it goes through some very complicated dance here, including some little squiggle at the end. Okay, so those are the two inputs. Don't worry about how I got them. Okay, this is what happens. So what happens is the outputs kind of wiggle around, and 50 seconds later, they hit their target values, and they just stay there. So you get exact convergence in 50 seconds. 50 picoseconds, I mean, it depends on what your application is. Everybody see this? Now, by the way, the time scale is this. I mean, maybe I need to draw where that is. That's about right here. Okay, that's what happened. Okay, so that input basically gets you convergence. First of all, it's exact convergence, but it gets a convergence something like 20 or 100 times faster, something insane like this. Okay, everybody see this? Now, notice that the input you're using is not particularly bigger. It's not bigger at all. I mean, the final input you have to put in is minus 0.63. You never really go outside that range much. I want to say something very important about these two input signals here. No one can look at those and say, oh yeah, I was just about to try that. Okay, there's no way. Okay, so this is kind of what this class is about. So it's, I mean, this you would not have arrived at these two inputs by trial and error. Okay, you would not have done this with a proto board in your garage and a box full of different resistor values. Let me assure you. Okay, you could get someone who's pretty good at fiddling with dynamical systems, like a fancy pilot, and a pilot wouldn't do this either. Okay, so now I'll tell you the end of the story. I mean, so this is pretty wild. By the way, things like this can be repeated in many, many fields. You can repeat this in finance. You can repeat it in lots of others. These things will beat the hell out of anything you can do. I mean, if it's set up properly, intuitively. Okay? So this is kind of what this class is about, is this kind of stuff. By the way, I will tell you this. This stuff right here, later in the class, by the middle of this class, maybe a little bit beyond the middle of this class, if I show you, I wouldn't even ask you to do this on a homework problem because it would be too insulting to you. Because you would know, if I asked you, I'd said, look, show me how to find the inputs that move the state from here to here as quickly as possible and do it in like 50, whatever, something like that. It would just be insulting. You'd just say like, oh, please. It would be totally obvious to you. So, but I want to point out right now, by the way, if there is anyone whose intuition was good enough to think that this was the right thing to do, please speak to me after class. So the point is this is not obvious, okay? This is not intuition or anything like that. In fact, a very important skill in the class is going to be to explain things like this. What will happen is this will just come out, and it will be impressive. It'll be in this one. It'll be in other areas. It'll be in signal processing. It'll be in image processing. It'll be in machine learning. Very impressive things will happen. The problem then is going to shift not from doing this or knowing how to do this, but to explaining it to somebody. And I'll spend some time periodically through the class explaining how to do that. I mean, how to do this. You can make a very good story about it here. You can look very smart. The truth is, you wrote about 4 lines of code to do this. That's about what it is. But you can get a lot of mileage out of it. You can say, yeah, it took me a while before I realized you really had to start in the other direction. That's the key, you see. Was starting in the other direction. Then, for a while, I couldn't get this middle section right. That was tough. Then I realized finally this one should bump down, sort of like it's going to the final value, but no, it's just to fake out the system because then you come back up here, you see. And all right, so anyway, that's going to be very important, okay? You'll see. So you'll see. That's an important skill. Maybe we'll put that on the final exam, something like that, where we'll have a section where you have to you'll have done something cool and maybe image processing or something, and then after that you have to explain it to someone. And we'll grade it on how plausible it sounds. Okay, it'll all be made up, of course. You did it by writing 5 lines of code, but okay. All right. Now it turns out here, if you can get exact convergence in 50 seconds, how about like 20? Well, you can do 20 as well. And now, if you go to 20, here's what's weird. You now are using a bigger input. Okay. And now, by the way, I'll show you something cool. The first thing you do has now shifted. Again, now the first thing you do is you go down, which is going to be the ultimate way you're going finally. And here you kind of go up. And anyway, so then again, you'd have to make a story about that. You'd say, oh, that's totally clear. Why? Because now you're doing it faster, you see. And so anyway, you make up some plausible story about that, which the gullible would buy. Okay, so this raises questions like, how do you do that? How do you find something like that? And how do you analyze this trade-off between the size of U and the convergence time and things like that? So you will know all of that. I mean, this will be, as I said, this will just be so obvious to you 6 weeks from now, it'll be insulting to even ask. Okay, we'll look at one more example. This one is from estimation and filtering. So here it is. And this is, if you have a background in signal processing, fine. If you don't, like if you're in some other department, don't worry about it. So we have a system. It looks like this. It might be part of a communication system, for example. And it's going to work like this. An input comes in. It's piecewise constant. And we'll make it a period of 1 second. But if it's a communication system, this might be nanoseconds or something, or picoseconds, or whatever. It just depends what this is. Yeah, maybe nanoseconds or something. So an input comes in. It gets filtered or convolved with a linear filter. That's a second-order system with a step response that I'll show in just a minute. And again, if you know this material, great. If you don't worry about it. We'll come back to this. So this is essentially a smoothed version of this. And now the interesting part comes. It's going to be very crudely quantized. It's going to be quantized with a 3-bit quantizer. Okay? There's only 8 distinct levels that it knows. Okay? So here's this thing will run at 10 hertz, even though the input signal is constant. So here's a picture that just kind of shows how this works. So the input here, is 0, and then it's got some value, but it's constant for each interval, which is 1 second long. Okay? Now this runs through a filter with this step response, and those of you who remember undergraduate signal processing, if you took it, will know that this means that the impulse response is sort of positive and has a little wiggle here. But you'll look at this and you'll know what that means is it smooths things on the order of a second or so, maybe 2 or maybe 1 or 2, and it delays things a bit as well. And so here's this signal after smoothing comes out here, and you can sort of see a bunch of things. I mean, it's 0 here. We keep this 0 just to make it just to see, so you can see the beginning. And you can see this goes down. This goes down, sure. Then it starts going up. But you can see that the individual levels have kind of been smeared out and lost. OK? So, and this is, if you know something about communications, you know this is basic communications. You know, basically, if you're transmitting like a Boolean, you know, a signal with multiple levels, and it's coming out where you're reading it nice and clean, it means you're not going fast enough. That's what it means. So it means you should crank up the rate until things start getting hard to guess. Maybe this is too hard to guess because now you've kind of smeared things out. But you can see things. This, where it's two positives here, translates into this kind of big bump here. But if I gave you this, you would, it's not an easy way to estimate what this is. But it's going to get worse because the next thing we do is we take this and we quantize this to 8 to 8 levels. So that's 3 bits. And that gives you this sequence here. OK? Each of this is just 3 bits. And now comes the problem. From this, we want to reconstruct and estimate that. That's the problem. OK? And that's a basic problem in communications. It basically says, let's look at what our receiver, our A to D or whatever it is sending us. And you want to estimate sort of what was sent at the transmitter, because from that you can decode what the message being sent was. OK? So this is sort of very basic in communications or anything like that. So the basic approach would be something like this. You ignore the quantization because it's actually, you just consider it some imperfection that is beyond your control. And what you do is you design an equalizer for this. Now an equalizer is another convolution system, and it has the property, and what you want is you want to kind of undo, or I guess in, for example, geophysics, this would be called deconvolution. So that would be another area. It'd have lots of names in different fields. You want to sort of undo the effects of the first filter. That's H. So you really want one so that GH is about 1. Again, if you know what this means, great. If you don't, that's fine too. So once you find such a G, that's called an equalizer. In communications, it would be called an equalizer. And you'll simply apply that to the received signal to approximate U. If you do that here, it will work hideously. It just simply won't work. You won't get anywhere near close to estimating these quantities. And then if you went back to someone who does traditional signal processing and say, what's wrong? And you'd say, well, come on, give me a 10-bit A to D, and we're talking. But a 3-bit is not going to do the trick. Everybody see what I'm talking about? So, OK. Well, now it turns out this problem can be posed as a basic problem you'll see in this course. Again, maybe around the 5th, 7th week, something like that. In which case, it'll be just completely standard for you. This one could be a homework problem. I mean, just to set it all up and do it. Maybe it will be. And if you do that, here's what you'll get. This is an expanded picture. If you make it an estimation problem, again, you will write something on the order of 5 lines of code. You will carry out some simple numerical linear algebra computations on it. And here's how close you'll get to the signal that was transmitted. The dark one shows the actual signal, and the dotted one is our estimate. Now, the one thing you notice here is that you get pretty close. I mean, you get amazingly close. And in fact, you might ask, how well are you doing? And the answer is that the RMS error, the root mean square error, is about 0.03. Now, that's super duper interesting because the quantization levels, each step is about 0.25 wide. OK? So that means the quantization errors are like plus minus 0.125. And we are predicting it better than, I mean, roughly speaking, better than 4 times the range of the quantizer. Are you disturbed? Who's disturbed by this? Good. You should be disturbed. Now, for the rest of you, why are you not disturbed by this? This is weird. I think there's something wrong with your intuitions or something like that. But no, I mean, come on, you got to admit this is kind of weird, right? I mean, I give you this measuring device that basically makes errors of plus minus, let's say, 125 millivolts. I give you these measurements. I mean, that's very crude. And then you go off and do something, which you'll know how to do, let's say, the 7th week. and you come back, and you actually estimate what happened from those crappy measurements, you actually get something that's 30 plus, that's typically off by around 30 millivolts. You're still not disturbed, I can tell. You're just like totally okay with this. Is that, well, someone, what, is this okay with you? You're like, cool, that's fine. Is that, why? Oh, okay, so you already bought the whole package and everything. Right, okay. All right. So, but no, yeah, you'll know how to do this, and you'll yawn, I mean, by the 7th week at things like this. But, okay, but you already bought the whole package, so you believe it all. So, yeah, I'm going to fix you guys. I know what I'm going to do. I'm going to come in with something that's totally wrong. I will say it with a totally straight face, and we'll see how far I can push. You better be on your toes. That's all I have to say. Okay, all right. All right, well, since you're not upset by that, I mean, you know, if it's just like, okay, cool, fine. Theory can do anything. But, we'll just move on, and we'll actually start the course proper. I mean, unless there's some questions, or this would be a good time to answer any questions about, I don't know, the basics of the class, or what we're going to do and stuff like that. So, okay. Oh, I do have one question. How many people here, we are going to use MATLAB. I'm not a huge fan of MATLAB, but we're going to be writing, you know, the key is you're going to write very short things. Actually, how many people here sort of have used MATLAB before at some point? Okay, so I think that's a whole lot. We are going to be, so you'll be fine. The stuff we're going to be doing is going to be very, very basic. If you ever write a script longer than 15 lines or something like that, or, you know, I mean, if the main part of it is more than 15 lines, you're probably doing something wrong. So it's not, I mean, the key in this class is that the ratio of thinking to programming we want to be very high. So if you find yourself writing 5 pages and if you find yourself doing anything that you could actually describe as programming, you're probably approaching this the wrong way. Just to let you know. That's generally defined as more than one screen of source code, I would say. So if you're on that 2nd or 3rd page, something's wrong. So that's part of the class. For those of you who, I mean, I think a lot of this you can just come up to speed on yourself, but maybe we'll convince the TAs if some of you want to just sort of have a quick introduction if some people need this. So, okay. So let's start the course proper. I should say about the course. The first couple of lectures are going to be review. So if you have an exposure to linear algebra, you will think it's embarrassingly and insultingly elementary. So, but don't worry, we'll get there. It's a little bit boring, and it picks up somewhere around, you know, it'll pick up in a couple of weeks. So, okay. So we'll start with the idea of linear functions and examples. And this, you know, presumably you've seen before. So this will just be review. And what I will do, though, is focus on sort of what the meaning of all of this is, which is, and what the implications are. And that's the part that is traditionally left out of a linear algebra course, a traditional one. Okay. So let's suppose you have a system of linear equations. So this is, you know, linear equations. So you have y1 is a11 x1 plus a12 x2 up to plus a1n xn. And then you have a bunch of these equations. In fact, we have m of these equations. So these are, everything you see here is a scalar. Well, you don't get very far, it turns out, by using complicated notation all the time. So it's actually, with matrix notation, this goes down to 4 ASCII characters, which is y equals ax. Now, here, y is just the vector of these y's stacked up to make a column vector. X is a column vector of these x's. And A is this, this matrix, which is m by n. So that's, I mean, this you should have seen. So this is the matrix form. And you should understand, in fact, that's kind of a theme in the class. I mean, so what's actually gone on here is we're heavily using overloading here. So everyone knows what y equals ax means when these are scalars. And here we have overloaded that to the case where x is a vector and a is a matrix. Okay? So that's the idea here. Okay. Now, this you've also seen, I hope, presume, guess, that you've seen the idea of a linear function in lots and lots of courses, I hope. But here's what it is. A function is linear if f, the function, which maps Rn to Rm, this notation means that this function accepts as argument an n vector and returns an m vector. This says f of x plus y is f of x plus f of y. You know, these, when you read these things, I should add, they're very easy on the eye because, you know, it just looks super simple. It kind of looks like just the plus went in a different place. It's just not that big a deal. It just looks very casual. It looks pretty and simple. This is actually making a very strong statement. This statement. And in fact, I think I'll do this once. Yeah, I'm going to do it. So we'll do it once. It's actually very useful in the notation we're going to be using to make sure you can parse what you're looking at. And in fact, for everything you write, you better be sure you can parse what you're writing. Because a parsing error, a syntax error is a bad thing. Let's look at this. So first, let's actually talk about the data type. So if I presume you've all had a class in basic computer programming. So you might want to think about the actual data type of these things. So let me just ask a couple questions here. What is the type? What is x? Is it a matrix? Is it a number? What is it? It's an n vector. Okay? All right, then what is this plus? What plus is that? What plus is it? It's vector addition. So plus is being overloaded here. I mean, everyone knows what plus is between real numbers, complex numbers. This is plus between vectors. That's an overloaded plus here. What is the data type of x plus y? It's a vector. It's an n vector. All right, f is a function. Now you can do the syntax check on f. F is being passed an n vector. Is that correct? Well, sure. That's what this says. It says f has been declared to be a function that accepts as argument an n vector. It is being passed an n vector. And so what is the type of what is the return value? M vector. Okay. What plus is this? Yeah, which vector addition? Precisely. That's m vector addition. Okay. And what equals is that? It's m vector equals. Okay. So all of this is heavily overloaded. But I'd encourage you to do this because otherwise what happens is you start writing stuff down. They're very short formulas and they look pretty and beautiful. But watch out because the point of powerful notation is precisely that you can write totally innocent looking things down that are 5 lines and they'll actually be saying a lot. I mean, that's the good and the bad news about it. Okay. The second is that f, you can scale x either before it's operated on by f or after, and you get the same thing. So a lot of people write this way. Alpha x plus beta y equals alpha f of x plus beta f of y, like that. That should hold, and that's one of the definitions of linearity. Okay? So, and this is a picture. Basically, actually what the picture says is this, and by the way, this is really stupid. It already has major implications. I mean, I guarantee you I can dress this up in some story where it won't look like this, but it will be about this. And it will have serious implications in that context. Okay, so here, what it says is this. You have a vector x and a vector y, and x ends up getting operated on and comes out over here. That's f of x. And y gets operated on and comes out over here. And the question then is, what would happen if this vector, which is the vector sum of x and y, were passed to f? And the answer is, you can find that 2 ways. You can either operate on this point with f, in which case it will come out over here, or you could actually take these 2 things and add them and come out over here. This, by the way, already has lots of implications because, for example, if f is a simulation, this says you actually can make 3 predictions at the cost of 2 simulations. Everybody see what I'm saying here? I'm assuming the simulation is expensive, but vector addition is cheaper. So, okay, but this you should have seen. That's a linear function. And here are some examples. Here's one. Here's a function. It takes as argument a vector x, and it multiplies. This x is in Rn, and it multiplies by an m by n matrix, and that multiplies something that's in Rn. That's an explicit function where I fixed it. It's parameterized by the matrix A. Turns out that's a linear function. You can just check very quickly. But here's the cool part. That's actually all the linear functions. That's a generic form. It turns out if a function is linear, it has to have the form f of x equals ax. Okay? Now, when you look at that, it looks very sophisticated and, you know, complicated and mathematical. It's actually not. It's actually quite straightforward. But I think I'll say one thing about it, and then we're going to quit. It's actually quite straightforward to work out what A is. And this you should think of, I think this is on your first homework, you should think of this as someone putting on the table in front of you a black box with a bunch of BNC connectors on the left, in fact specifically N on the left, and a bunch of N BNC connectors on the right. And then you're just in a lab. And the question is, how would you make a model of that box in your lab slot so that later, when you're not in the lab, you can actually predict what it will do, actually for any input. And of course, given that it's linear. So, okay. So I think we'll quit here and then continue on Thursday.